Okay, we're going to start off by talking about expectation, variance, and covariance. These are important concepts. You'll see that variance rears its head throughout the quarter in all manner of applications. And it happens to be really important for what we're going to talk about this week. Many of you probably are already familiar with the concepts, but I feel like it's good to get us on the same page. So let me share my screen and get going. The first thing we'll talk about is expectation. By this we mean mathematical expectation. Really, it's just a fancy way of saying an arithmetic average, okay? And we all know how to take an arithmetic average. It's a slightly more general way of taking an arithmetic average, okay? So suppose we have a discrete variable that can only take on, discrete numbers of variables, right? So like one, on counting numbers, for example, not continuous numbers. So we have the expected value, and I write this kind of funny crosshatched E for expectation of a random variable X is equal to the sum across all possible values of this random variable X, which we're going to index with the index I, P sub I times X sub I. Okay, and what is P sub I? P sub I is the probability of observing the ith value of X, okay? And it is a probability mass function, okay? And as a proper probability mass function, the sum across all I of P sub I is going to equal 1, right? So this is just an average, an arithmetic average for a random variable. And, we know like the sample mean that we all know how to calculate. We have a sample of n items, right? And our average is just 1 over n times the sum of those averages. So what we've done is we've assumed that our P sub i's are all equal to each other, and they're equal to the inverse of our sample size. Okay, that's where the sample mean formula comes from. It comes as a generalization of this. Okay, if we had a continuous random variable, our expected value would be equal to just the integral. And we'll say that the integral is done over some range, we'll call it capital omega, because it's going to vary from different types of variables, right? So like, for example, a normal distribution, your limits of integration are from minus infinity to infinity. Whereas if you have a log normal or gamma distribution, it's going to be from 0 to infinity or something like that, right? There are going to be different limits of integration for different random variables. And we'll call the probability that f of x, in keeping the standard statistical notation, right, was f of x is the probability density function of x with respect to x, okay? So just to be consistent, this is the probability density. Especially in this first week, all the expectations we're dealing with are discrete, so we'll be focusing on this formula here, okay? And we often, indicate the expected value of a random variable by putting a bar over it, right? X bar. And sometimes you'll see, and this is true in some of the in some of the readings, the expected value is indicated by the Greek letter mu. Okay, good. Next, let's move on to variance. It's closely related. Variance. Okay, and what is variance? Variance is actually, so the variance of a random variable x is actually equal to, it's the expected value of that variable minus that variable's mean squared. Okay, so the expectation of x minus the expectation of x, that whole thing squared. Okay, that's the definition of variance. And it's essentially a measure of the spread of a random variable around its mean. Okay, and it's obviously a symmetric spread because we're squaring it. Okay, let's do just a little bit of algebra, and what we'll find is that we can come up with a much more useful formula for actually calculating expected values, and that it'll allow, or variances, it'll actually allow us to see some identities in some of the things we're working with, possibly. I actually don't remember, but it's always good to look. All right, so the first thing we're going to do is we're going to expand this. We're going to multiply it out. Okay, and so the expected value of x squared minus first outer inner last. So it's 2x e of x, expectation of x, plus the expectation of x squared. Okay, and now we're going to use the rules of expectation, and in particular, we're going to lean heavily on the linearity, which tells us, so the expectation of x squared is just the expectation. Is just the expectation of x squared. Okay, now we'll use linearity to tell us that the expectation of 2x is just 2 times the expectation of x, okay? So 2 times the expectation of x times the expectation of x, right? Plus the expectation of x, the quantity squared. All right. So now we can factor this again. Okay, so what we get is let's see, where am I? Oh yeah, it's simple. It's just the factorization of this is just the expectation of x squared minus the expectation of x squared. It's confusing. All right, so this is a very handy formula that we will see. Maybe one sees it in population biology and economics and demography, but I think it's useful to be aware of it. Another related quantity to variance is the standard deviation. Okay, and the standard deviation, which we often signify, that's, believe it or not, that's a Greek letter sigma, is equal to the square root of the variance of x. Okay, which, and we often call variance by the Greek letter sigma squared. Okay, well, it's not a Greek letter. I mean, sigma is a Greek letter, we square it. Okay, so the standard deviation is sigma, the variance is sigma squared. Okay, now we'll move on to the last topic for this video. And let me just shift my notes, which are lurking over here, which is why I keep looking over here. They're useful. Covariance. Covariance is at the heart of the price equation, and it's at the heart of selection. And so it's a really important thing to have, and it's probably a little less familiar than say a mean, an arithmetic mean or an expectation, or variance. Okay, so the covariance between two random variables x and y is equal to the expectation of the product of these differences. So it's x minus its expected value, so x minus the mean of x times y minus the mean of y. A lot of parentheses there. Okay, it's just the expected value of this product of the differences between the two values and their means. Okay, once again, we can do a little algebra to make this more useful, and this you definitely will see because we use this in deriving the price equation. All right, so the expectation of xy minus x times the expectation of y, we're just multiplying these factors out, right? Minus the expectation of x times y plus the expectation of x times the expectation of y, running out of room. All right, and so now we're going to distribute our expectations around like we did for the variance. And we're going to use that linearity rule for expectations. So the expectation of xy, all right, minus, and once again, the expectation of x is just the expectation of x, right? Expectation of x times the expectation of y. The expectation of an expectation is just the expectation. So the average value of an average is just its average, because that average value is just a single value. And just like in the variance, the average value of 2 is 2, the average value of a single value, like the average, right, is just going to be that average, right? And then minus the expectation of x times the expectation of y, right? We're taking the expectation of that, plus the expectation of x times the expectation of y. Okay. What we see is that we've got the expectation of x times the expectation of y minus here and plus here. That means that these guys cancel out. All right. And what we're left with is the covariance of x and y is equal to the expected value of their product minus the product of their expected values. All right. And as I said, this will be used when we derive the price equation. And I should say by we, I mean I, when I derive the price equation and you look at the video, I'm not going to ask you like on any problem set to derive the price equation. This is informative. It's not, this class isn't about, it isn't a math class. We're not going to be doing derivations of things to test you, okay? And just one last thing I want to draw your attention to. Covariances can be kind of hard to interpret. They're really important theoretically. They can be kind of hard to interpret because they depend on the values of your random variables, right? You can have something that two things that really covary a lot, but because their values are low, right? They have a lower covariance than something that, has big values, right? The covariance between like brain size and body size in a pygmy shrew population is going to be much lower than the covariance between brain size and body size in African elephants, right? Because the African elephant's body size is orders of magnitude larger. Okay, so we often want to standardize this. And the way we standardize this is to calculate a correlation coefficient, okay? So rho of x, y is equal to the covariance of x and y divided by the product of their respective standard deviations. Okay, hopefully this is helpful. Hopefully it's a review. It's always good to know about expectations and variances and covariances. You're going to find that this is a class about variance. Variance matters for everything in adaptation and risk management. We're going to come back to variance again and again and again. And covariance is kind of a special case of variance. Note that if the random variable that would, here we go, the covariance of x with itself is just equal to the variance in x. All right. So it's really important to understand what variance is. It's good to know these identities, such as this one here. It's good to know this identity here. We're going to use it. I'm going to use it in deriving the price equation. All right. Understand variance, and we'll take it from there. See you in the next video.